Okay. Does it say it's recording? This in the top? Yeah. Okay.
Yep.
All right. So last week we had a fairly broad and I guess hand-wavy introduction. So the way I like to think of it is it's not really a course or a tutorial so much as I want to sort of remind myself of some of these concepts eventually to get to where we can use them for specific modeling purposes and for thinking about the mind, even if you like, or at least cognition and perception. And so in order to, and one nice thing about dynamical systems is that the qualitative is a big part of why we use it. So the math is definitely part of the story, but one of the big selling points is that you can derive some qualitative insight into a system from a mix of math and geometric or pictorial thinking. And a lot of people, particularly in biology and neuroscience, end up hearing this terminology, catching it, from here and there, but not quite, never looking at it. So I feel like going over it is good for people who already know it, and for people who don't know it, you don't have to feel uncomfortable and nod along. You ask any question about anything, including notation or what this symbol means. Feel free. Okay. So I showed this before, but this is just what we're going to do today. So we'll just, for once and for all, define a few terms. What is a dynamical system? What is an attractor and a repeller? Bifurcations we'll probably only talk about tomorrow. Next week. We'll touch on what cost/energy functions are from the dynamical systems perspective. And this is what I mentioned last time as long-term goals. Some of them we'll do more soon, but it would be nice to link some of this with perception and phenomenology. Some of my work in psychiatric disorders has already been linked with dynamical systems. And then there's more far out things in the zone of emergence, and eventually the even more far out concept of agency, far out for some people. And eventually I will add to the Strogatz with a little of Itzikovich. So I think after a couple of weeks, maybe after we do the chapter on bifurcations and one on 2D analysis, we can look into, I figure maybe in one section we can talk about the Hodgkin-Huxley system, just qualitatively look into the experiment, then look at the Fitzhugh-Nagumo reduction of that 4-dimensional system to a 2-dimensional system, and see what sort of insights you can get from that. So that may be, let's say, 2 or 3 weeks from now. So what is a dynamical system? It's Wikipedia is handy. It defines it in physics terms and mathematical terms. So you can think of it in terms of a particle or ensemble whose state varies over time. And so it obeys differential equations, which are defined by derivatives over time. And for now, we're going to deal with continuous systems, so not discrete time. And in mathematics, you have a slightly more general version of that idea, which is that it's a system where a function is describes the time dependence of a point in a geometrical space. So I just sort of laid out here what that will end up looking like. And it's always good to keep in mind, it's sort of, you don't always catch it necessarily, but when you have multiple axes, the space that we're talking about usually doesn't include time. So the dotted lines that I drew here are just sort of pointing out that time will be a sort of video you look at on top of this space. There are situations where you will show time in there, but that's not the state space typically. So that leads to the question of what do we mean by dimension? For particles in space, it's fairly clear. It's a spatial dimension. So it could be your XYZ coordinates, or it could be in a radial system, a distance from a center and an angle. It could be another quantity. For us in neuroscience, very often it's voltage or something more abstract like firing rate, or it could be just a count like number of people, number of entities, number of cells, or densities, things like that. You'll often come across the word degree of freedom. So the specific terminology will depend on the field. So it's always good to double check when someone uses the word dimension, what they mean. In fact, a couple of years ago, there was someone who did some fancy data analysis, and there was this pop science article saying that neuroscientists find a multidimensional universe in the brain. It was an extremely cringy, even by the standards of pop science, um, way of writing a headline, because they were sort of playing on the fact that most people think higher dimensions means higher spatial dimensions, and very cynically using that as clickbait. Because if you understand dimensions to mean the measurables, then the fact that there are large dimensions in the brain is not surprising at all. So the space created by the dimensions or degrees of freedom is an abstract representation of possibilities, and it's typically called a state space or a phase space. So physicists will usually call it a phase space, but sometimes the word phase confuses people because of the relationship with angle, phase angle. So I like to use state space more, but again, when you come across these terms, always check what people mean. In artificial intelligence and machine learning, feature space is often used instead, specifically to talk about the data set. So the feature set doesn't include the degrees of freedom in the model. And a lot of interesting discussion has to do with how complex the model is compared to not only the dimensionality of the data, but the sheer number of examples. Some of you may have heard that machine learning is approaching the point where it's able to not only generalize, but also remember every single exemplar. In the case of millions of faces, in some sense, all the faces have been remembered individually because of the sheer number of parameters. But that's something we probably won't talk about anytime soon. So just some bookkeeping. If a single component of a system, which could be a particle or a neuron or something, has a certain number of dimensions, and there are n of those identical components, then you have n times d dimensions. And that's where you get, in classical physics, you start from classical physics, you get these 6 degrees of freedom, which is position and velocity or momentum. And from there, you get 6 n dimensions, where n is on the order of Avogadro's number. So in StatMech, you'll see that kind of thing. So yeah, things get hard to visualize, or impossible to visualize in some sense, above 3 dimensions. And even in 3 dimensions, showing something in a publication that where it's a projection of a 3-dimensional in 2 dimensions, it does create a lot of confusion. But there are ways of projecting back down. But you always lose information when you project some higher dimensional entity onto lower dimensions. So it's worth keeping that in mind. Again, I thought let's just really go through the qualitative basics, and here's where anyone who feels embarrassed about or whatever, don't feel embarrassed, ask questions about this sort of thing. So most people, I think, are familiar with the idea of derivative as a rate of change, and some of you probably remember thinking about a derivative as a tangent to a curve. Does everybody know what a tangent is? If anyone doesn't know, we can elaborate a little bit on that. So I'll just say, when you have a curve in a continuous system, the tangent at a point can be understood as a straight line that touches that point. And for a smooth curve, the tangent is unique, and it's given by the derivative, basically. So there's a spatial way of interpreting derivatives in addition to this rate of change idea. And if you look at some of those 3 blue, 1 brown videos, you'll get some of this intuition. I highly recommend those videos, by the way, even if you've already taken plenty of calculus. But a thing to keep in mind with tangents is that they're not defined when you have a discontinuity. So in this case, This blue line, imagine that's some process unfolding, let's say, in time. Uh, that you can't really define a tangent when there's a discontinuity like that, because infinitely many points can touch on that point. So that's one way of thinking about why discontinuities are badly behaved in the context of differential calculus or prediction more broadly. Is that clear? Just ask if there's anything you'd like to zoom in on, because we can always go over it. So diving right into the Strogatz book, so basically any system, we talked about this a bit last time, but basically there are the order of a differential equation is the highest derivative. So we're going to be dealing with first order equations which have only a single derivative. So acceleration is the second derivative of position. So velocity is the first derivative. And we're going to be dealing with one-dimensional systems for now. So there's only one quantity. And so the dynamical systems will be governed by an equation involving the derivative and some function of x. We, for now, don't talk about explicit time dependence, which is a different, slightly more complicated situation. So Strogatz talks about a hypothetical problem where the speed of some x, you can imagine it as some kind of position. In fact, one of the problems is to kind of interpret this physically. But so the first thing we do is just plot what this is. We know it's a sinusoid, so it's an alternating curve alternating between positive and negative. Did anyone think about a good physical interpretation of what a relationship like this might mean or might look like? It could be a very toy problem.
You could think about this as gradient flow for a circle for the height function.
For the what function?
For the height function, just the function,
okay.
the vertical coordinate here.
Right.
Write that as like sine of the angle with some shift, right? And then this is very common in like geometry to think about spaces in terms of like you draw the space and then you think about what the height function looks like and you look at like where the critical points are. So there's one at the bottom, which is like the stable one that everything like ends up at, and there's an unstable one sitting at the top.
Right.
My favorite example of that is the reflector on a bicycle pedal. If you see the reflector on a bicycle pedal going around, if you're directly behind the bicycle, you'll see it going up and down at that speed because the person bicycling.
Excellent. So when you have, that's a good example. I guess another, you could imagine x is the angle and you measure the angle with respect to the horizontal. So the maximum speed is, and imagine that it's a bowl, but with a lot of friction, and friction will become important. We'll talk about that a little bit more later. But imagine if it's something that has its maximum speed at the bottom, then you can sort of think of it this way. It wouldn't exactly fit with gravity exactly, but that's one way. So basically, these arrows point to where the system, which is now just this one variable x, will tend towards. And since you know the sign of it, that gives you all the information you need about where it goes. So this is an example of that qualitative understanding. Just knowing the signs will, in this case, can tell us about these points, or basically the points where direction changes.
I have a question here.
Yes.
So can you talk a little bit more about the axes? So for example, on this bicycle pedal example, if you had a position in space, normally we think of like an X position and a Y position, but here we're only having one spatial dimension, and then what's being plotted on Y, that's the derivative. How does that work? Can you explain a little bit about that?
Right. So we're looking at how the speed of that quantity varies with its position. So that's what we're plotting on the y-axis. And since those are the two things that that we're basically given and we're interested in, we can look at how both of those things intersect with each other and with zero. Because zeros are interesting because that's where motion stops, because the derivative goes to zero. And when the derivative goes to zero, so in all these diagrams he hasn't marked it, but this cross, the center of the plus sign is zero and for both axes. What can you say about those? If the system is exactly at one of those points, what can you say? So if something is here, what happens at this black dot? So let's say something's at this right on this black dot. What would you expect to happen?
Nothing.
Basically, yeah.
Would that correspond, if you were in a car following a bicycle, watching the pedal going up and down, would that be at like the top of the pedal or the bottom of the pedal, right? It would be one of those two, would be that black dot?
No, neither one, because that is a two-dimensional system, as you were saying. So this is so we're only talking about a one-dimensional system here. So I heard a good example of this at one point, of one of these one-dimensional systems, and that's just a light switch. So like when you have like these like flip up down light switches, like either side, so like the top, like the lights on or the lights off, right? Those are like some types of these fixed points, but then also there's a point in the middle where you can kind of like where it's a stable, where it's not a stable point, but if you move it a little bit, it's going to go one way or the other. So that's I think a decent example of this.
That's a really good example. Yeah. You can,
probably
now that
the best physical example of a function like this would be corrugated metal roofing. If you take a piece of that stuff and lay it flat so that there's no gradient parallel to the grooves, you're just talking about the grooves. Then you put tiny little massless bits of styrofoam on it at different places and see which way they roll.
That's one way to think. So I think the light switch is a better example than the bicycle, because bicycle is first of all driven, and it's what you're really looking at is constant angular velocity if the person is pedaling at a fixed rate, in which case it's not a speed that is dependent on the sinusoid.
I mean,
so,
you could have a bicycle going in a spiral in, spiral out. I mean, it's changing, right? So if you have a spiral, like a concentric circle, let's say the radius keeps changing, so the angular velocity at every point keeps changing. I mean, I don't know if it's a very good example,
but I think versions of Rob's example are the easiest. So imagine a stick or a lever that's pivoted at the center. To keep the convention right. So the maximum, so sine 90 is 1, and sine will do.
It was always taught to me as a rigid it's just a height function of a rigid pendulum.
So with the pendulum, you kind of want to keep the second derivative and talk about, and the fact that the pendulum has momentum means that it's not an
true.
example.
I mean, yeah. Okay.
Because that's a second order system. So later on, he gives an example of something like that with a whole lot of friction. And when there's a lot of friction, you have an overdamped system where you don't have momentum, and maybe we can talk about that.
So just to clarify the bicycle wheel example, I was talking about the one-dimensional. If you're on a car directly behind a bicycle and you can only see the vertical dimension directly behind it, the reflector that you're looking at, say it's night, will just be going up and down, like pumping on a single vertical axis. So it's one-dimensional.
Well,
right?
okay, so that's so it's really a two-dimensional system that's being projected onto one dimension. So
Exactly.
that's a little bit different than this,
Okay.
where the dynamics are actually living on one dimension. They don't have that second degree of freedom to move around in.
Well,
Okay.
forget that. The motion is totally different because their x is like sine of t, right? Like that describes the motion of this light on this one axis. But if you take sine of t and you take the time derivative, that's like cosine of t. That's not sine of t, which it would have to be to solve this equation. So the
This
fact
is a very
that
good point.
sine of x, not sine of t, is like the crucial difference.
Yeah, so I'm glad that we paused on this, because the key here is that this is sine of x, not t. So what that means is that you should interpret x as an angle and not as something that is moving in a circle, ideally. There may be situations where you can make it work that way, but this, I really like the light switch example, or a stick that's or pivoted on a hinge at the bottom that falls faster and faster as the angle increases. That one, with these kinds of things, you just have to work out the convention of what you're taking the angle with respect to, just to make sure that 90 is the maximum and 0 is the minimum. But that's just the geometry part. Does that I really like the light switch example. Could anyone come up with more? Or do you want more?
Strogatz talks about taking physical systems and putting them in thick motor oil or
Right.
honey or something like that, which I think, all these things we've been talking about would map onto the picture that you've got here better if they were immersed in thick motor oil.
Yeah, I think I come to that. But yeah, I think part of that helps with physics students, especially because, physics, classical mechanics 101 students have all been taught the simple harmonic oscillator. And here we're talking about something that is in some ways simpler than that. So otherwise people don't necessarily have all that much intuition about springs and goo.
I think the thing that would be helpful is if you just draw x and t for the, I guess that's what you're doing now,
We're
right?
going to do that very soon. But the idea is that you should be able to have some intuition about what will happen if you have intuition about what the black and white dots are like, vaguely. So so you know what the shape of the sinusoid is. So you know that what's happening is the velocity will reach a peak and then it'll come down. So as you're reaching 0, it kind of gets, the rate at which it comes to 0 changes. So it's not a linear speed up and slow down. So another way to think about it is, obviously when you're at the black point, one of the black points, because the derivative is always pointing towards it, it'll just stay there. What happens when you're exactly at one of these white points? It will
Nothing.
still just stay there. Ideally, in this ideal kind of model, which if you would implement it and place your initial condition there, it would stay there. In the same way that something poised at the top of like the light switch can be made to stay right in the middle. But it won't really stay there for long, because any small perturbation will make it move to one side or the other. And that's kind of, and we'll come to that way of thinking more explicitly.
Is it worth highlighting the diverse terminology that's used to describe fixed points? There's just a handful that come to mind, like people talk about steady state solutions, time independent solutions, equilibrium solutions, and fixed points, and they're basically synonyms. So depending on which field you're in.
Yeah, and did you mention asymptotic solution? Because that's another term that may come up. Because sometimes it takes infinitely long time to reach the fixed point, but that in practice ends up being not infinitely long. So when you oops. So what we're doing here is imagining that we start at pi over 4, which is a quarter of the way. So somewhere over here, wait, somewhere over here, and ask, well, what happens if we just let the system go starting from that point? And just by looking at the arrow, we know that it'll head towards pi. That much we know just from the arrow. With the shape, you need to kind of look at the shape of this curve and say that, well, initially it speeds up a bit, and then the velocity, the rate at which the velocity changes slows down. So then it tapers off, and eventually it isn't really moving anymore by the time it comes here. So the velocity it's still positive, but keeps reducing. And when it reaches the fixed point, it's not moving anymore. And you can do the same thing because it's periodic, you'll have a similar pattern around pi and minus pi. And an attractor means it will be that way on both sides. So whether you're above or below pi, over time it will converge on pi. Whereas from the perspective of 0, however close you are, eventually it will drift away. And that's what this means, that the arrows are always pushing away in the neighborhood of those points. So now we had a little bit of discussion about what an attractor is, but there's a nice clean definition. It's consistent and includes cycles. An attractor is a set of points in the state space that the system will tend to approach and will arrive at given enough time. So this is a loose, informal definition, but if you go to Scholarpedia, there's a nice formal definition if you like that sort of thing. If the system is already in an attractor, perturbing it by a small amount causes the system to return to the attractor. So we've already kind of covered it, but you can just now make an equivalent definition of a repeller. Would anyone like to do that? It's just basically the same sentence with a few things tweaked. And we already talked about what happens when it's exactly at the repeller. So we can just move on. But it should be, I mean, it's clear to everyone what a repeller is, right? Okay, so now we can kind of zoom in on this concept of perturbation. And one thing that struck me is that partly because of this emergence discussion group, a lot of the time we were talking about scale and what counts as something small and something big. Because very often you see in the discussions of emergence, this concept of levels or things that are much bigger than each other. So even in something very simple like this, you can get a flavor for what you might think of as sort of natural units of regions in which certain things can count as very small. So based on what we just did, this is just another a random function I just drew. You can make claims about A, B, and C. So what's A, given what we just saw?
An attractor?
Yes, okay. And B?
A repeller, right?
B is a repeller. C is also an attractor. So for when we're here, you can get a sense of how big of a what's that point? Okay, So how big or how small does it need to be in order for a perturbation, meaning a small bump, to not bring the system back to A? Roughly going past this point, basically. Into that. So then we can look at this system. There's only one attractor. So the system is globally stable. From wherever you start the system, it'll always end up converging on this. I just drew these two. How about these 2 points? What are they?
These ones are marginal.
But they're both
Attractor and repeller.
Well, it's like attractive from one side and
And
repel.
repelling on the other side, right? So it's
repelling on the
oscillating.
other side, yeah. So those we'll deal with more when we talk about attractors. Sorry, when we talk about bifurcations next time.
I guess you can say that a perturbation is small. You know, you kind of zoomed in the top right in a way that made the second derivative look small.
In the top right.
Yeah, so in the top right, it's like very stable. You can do a large perturbation. But what you're worried about is like perturbing so large. You know, basically what ensures the stability is the derivative, right?
Right.
So if your perturbations are small relative to the second derivative.
I see what you're saying.
The critical thing is they have to be small relative to the distance to the next fixed point.
Exactly.
Right,
That was what I was thinking.
And you don't really have control over that, maybe. I mean, it depends like how you're thinking about your system. But if we were doing a local analysis, we might not know that like we're in a stable basin that's like enormous, but we can at least get like a lower bound using the second derivative.
Right. Yeah. So this is an interesting, simple kind of insight that comes from this. So in one-dimensional first-order systems, oscillations are impossible. And you can kind of get the intuition just by thinking about this diagram and what happens when you reach an attractor. So the next very useful idea is what really people have in mind when they're thinking about dynamical systems is not just the directions of the various derivatives that for higher dimensional systems, for instance, but some notion of a landscape. So you may have heard of people talking about attractor landscapes and things like that, or you may have heard of Waddington's epigenetic landscape. This is a very common metaphor when talking about the dynamics of systems. But landscape in what? It's not the state space that we just saw, which talks about the quantity and its derivative. It's something else, which is not always easy to find, but in one dimension you can just calculate it. So this is where we were earlier talking about the difference between the spring and these one-dimensional systems. So the reason he has this goo here is because in second order systems where the second derivative is important, you have, the way I like to think about it is in terms of momentum, that even when it reaches an attractive fixed point, it'll go past it. And so it may take a little while in a dissipative system to lose enough energy to actually reach the bottom of a hill. We don't have to worry about that kind of thing when it's a first order system, first order one-dimensional system. So this is just a little bit of how the potential is used. So the insight is this idea that a system will tend to move downhill with respect to some hill. And right now we don't know what the hill is, but we're going to calculate one. We're going to say, can I find one that if I could construct a landscape, in this case, the landscape is over my one-dimensional quantity X. I want to find something which gives me like a cheat sheet for where the system will go given any initial condition. And here you can just calculate it by stipulating that your derivative with respect to X. So the function there is defined in terms of the derivative with respect to X, not time. So it's a spatial derivative, or the tangent with respect to X. And this negative sign is for a convention, is the convention that systems will tend to move downhill. And a good place to pause and point out that a similar metaphor is used in evolutionary biology, but with the sign reversed. So when evolutionary biologists talk about fitness, they talk about fitness peaks, because the goal, not the goal, but the tendency of individuals and species is to become more fit. Bad adaptations we'll leave out for now. So that's just a little thing to keep in mind. It's basically an upside down version of the same idea. Climbing a fitness landscape and moving down in some potential landscape. So just a tiny bit more math, because I just like these types of simple proofs. But how do we know that it'll always, the system tends to move downhill? Where did that come from? Is it a force? No, there's no force implied. It's something we just inferred from the dynamics itself. And it's just a little bit, it's a small algebra trick, but basically it shows that the derivative of that same potential with respect to time, which is what we're interested in effectively, is always negative. Or it can be zero also, and when it's zero, you have to deal with that. But that's so in one dimension, you have this very handy tool of calculating a potential directly. But in higher dimensional systems, it's often very difficult to find that potential. If you do happen to find it, it can be very useful and allow you to do all kinds of things. Okay, so any questions about this topic? We can pause here for a moment. I just have a few more things we can, like a couple of examples.
It doesn't have to exist, right? Like the equations you wrote are implicitly, you wrote them for a conservative system.
Which
right?
one? This?
No dissipation, for instance, no friction actually in this equation, unless you have a term for x dot that also, or a term, sorry, unless their force also depends on x dot. Right?
So
if you have like a drag.
Okay, that's a good question. Actually, I'm not 100%. So if it's a one-dimensional system and first order, can it be anything other than dissipative?
One.
It's not something I.
You can't have momentum in a one-dimensional system, right?
This is what I thought, right?
Well, this thing conserves energy. I don't think you can have energy conservation in a one-dimensional system either. It's kind of a confusing question for me because.
Actually, I think this thing does not conserve energy, because if you're at a place where the derivative of potential with respect to x is positive, then that means that the change of x with time has to be negative. So you're going to be going to the left, and eventually you get to a place where there's a flat bottom where the derivative is zero, and then the change of x with time is just zero.
No, v is not the thing that's conserved here. Like Yohan wrote down, v is decreasing with time, right? But v plus x dot squared over 2, you take the derivative of that with respect to time, you find that
but at the bottom of the valley where dv dx is zero, x dot is 0. So x dot squared is also 0. So the kinetic energy is also 0.
Right, you wrote x.
Once it stops.
Maybe I was misreading this equation. Let me see.
Yeah, I think you're just thinking too physically.
I think that
this is math here now.
Yeah, I think that that it's a sort of math way of going back to the physics is to say that one-dimensional, first order systems may not have conservation, but I don't know for sure about that. Conservation of energy specifically.
There might be something else that's conserved, but it wouldn't.
Right.
It wouldn't be energy.
Yeah, I shouldn't assume just because you write 2 equations, you wrote the Hamilton equations.
Oh yeah, it's definitely not a Hamiltonian system, right? So,
thank you.
Okay.
I have a question. Can all
Question.
1 or 2 dimensional dynamical systems be mapped onto some landscape?
Do all two-dimensional systems?
Yeah, like for any 2-dimensional dynamical system, could you construct a landscape to represent it?
I am not 100% sure that I don't know how to do the equivalent of this process when it's multivariate, when you have an X and Y, and whether there may be some underdetermination there, but Ryan, do you know how one goes about doing that?
I am pretty sure it's not true.
Meaning that you can't do it?
Yeah, so one way you can define a potential here, if you just have a one-dimensional system, you can sort of define the time along the flow.
Mm-hmm.
And sort of like, proper time is basically what the potential is measuring.
Okay.
Like it's once you measure proper time decreases at like a constant rate. But if you have a two-dimensional system, then you would worry about, say, cycles, where you no longer have a potential that really makes sense, right? But it's easy to set up just a vector field that's spiraling, right? And then the solution to the equations will include closed orbits. So it won't just be a gradient flow like this.
Right.
That makes sense.
That's a good point.
That's what you get from having 2 dimensions.
Right.
Mm-hmm.
Yes. So we'll come to the two-dimensional. We'll return to this. So we should like bookmark that question, and I'll look into this a little bit too. But I think that's basically, it's much more complicated. So right. Yeah. Anyway, a classic example of one-dimensional dynamical modeling is population growth. This notorious paper, which many of you have probably heard of, Thomas Malthus's paper on principle of population. What I didn't realize until fairly recently was how much impact this had on other people. Both Darwin and Wallace cited this as one of their influences in thinking about evolution through natural selection, because they looked at the prospect of exponential growth in a place with finite resources and immediately thought of extreme competition, survival of the fittest. So this is not true, but we'll get into that. So people looked at this this particular curve, which is exponential growth, which is the sort of continuous version of geometric growth, where each generation has same number, like 2 or whatever, any number. Then this is the continuous version of that. And you can represent that as this first equation, where n is the population, r is the growth rate. Is this the same as the R0 value for I don't know, but it's what R0 in epidemiology is one
I
of these
think
terms.
it is.
I think it is, yeah. Or something approximately in that zone. So that's the solution. And some of you may recognize that this as the equation that Kurzweil and gang used to justify the the technological singularity. The reasoning being that when you have a certain amount of knowledge, let's say the N stands for knowledge here, subsequent research is going to be a fraction of what's already known, and therefore you'll always increase and then have exponential growth. There's a few places where it looks vaguely like that, but some version of the same constraint probably applies, which is that when there's resource depletion, you expect a variable growth rate, meaning that R cannot be constant. And how that's modeled, one way is to think that, yeah, so this is just the qualitative idea that Strogatz points to, which is a nice way of kind of getting at how a physicist or someone with a applied math background starts to think about it. You initially start with this qualitative idea that R decreases, and then you say, well, what's the simplest way that I can get this R value, this growth rate to decrease, and the linear decline over time is the simplest thing you can do. And that gives you this equation, which is the logistic equation. That basically this factor of 1 minus n over k, where k is this concept of carrying capacity, is a way of dragging the effective R down. And you can do this similar analysis and say where the fixed points are. You should, I think some of you should be able to just look at that and immediately say what the fixed points are. It's not too hard. Set n dot to 0 and then solve that equation. So you can plot out what that looks like. And there you see a white circle and a black circle. So in this system, there's only one attractor marked out where n is equal to k. And so that's a stable point of the system. Strogatz points out that this doesn't really work that well apart from, I think, what was his, there's a handful of cases where it does work, I think with very simple creatures, but it's a much more complicated story for more complicated animals. But so it's not that this is the story of population growth. It's far more complicated. It's an example of where an approximate solution can help you start thinking about it. And in some cases, it'll work.
It certainly gets more complicated when you have more than one species. If you have two species, then you already have 2 dimensions, and then you can have oscillations.
Yep. And when we get to 2 dimensions, we'll do the Lotka-Volterra, because that also has a nice connection with how neural oscillatory models work. Okay. So if you want something a little bit more quantitative than just looking at the attractors in this geometric way, then the first pass kind of way of talking about it is linear stability analysis. I'm not going to go through the math, but if you want, we can. But basically, the idea here is that you imagine that eta is some small perturbation. So now we've been using the term perturbation. So what exactly do we mean by that? We mean a small deviation, in this case, from some fixed point x star. So this x star is some fixed point, and we're moving a little bit away from that in time. And you'll find that eta is governed by the same equation as x dot. And so then you can look at how this varies under certain assumptions, the assumption that it's very small. So I'm guessing a lot of you don't know what Taylor's series is, or have only heard about it in passing. Maybe later we can talk about it a little bit in more detail. But basically, there's a way of expanding functions using an infinite series that involves using a series of its derivatives. In this case, the derivative f dash is with respect to x, not time. And then there are arguments for ignoring higher order terms. It's called the big O notation. So in this case, in some situations, not always, when you write out this expansion, there are terms above a certain size that you can ignore because they have very small effects on the movement. So now we just sort of plug in some values that we know already. So why, this is simple, but why is f of x star 0? Because it's a fixed point. We're just putting in that knowledge there. So now what we've done is we have come up with what's called a linearization about x star. This is used all over the place. It's one of the, and it's very, very useful. You have to be careful about where it's applicable, and that's the big sort of art of it. And then when you solve that, you get something that you should recognize as that exponential growth / decay term. Whether it's growth or decay will depend on whether this derivative f dash of x star is positive or not. And since that governs how fast the growth or decay is, 1 over the absolute value of that is called the characteristic time scale. So with a little bit of approximation, you can start to get some quantitative insight into how stable the system is, and on what time scale does it, when you bump it, does it go back to the attractor? Or in the case of a repeller, on what time scale does it explode and go really, really far away? Okay. Oh yeah, this is just a little history of science side note, but a few years ago I found out that infinite series, which were initially thought to be a European invention, had also been discovered several centuries before in India, particularly for trigonometric functions and a few others. It's just an interesting thing to note. That's just all right. So this is just the diagram of what we just saw. That if we just look at what happens to the perturbations, then we know that if that derivative is less than 0, it will sort of rush back. And in this case, when eta goes to 0, that means you're back at the fixed point. And otherwise, if it's greater than 0, it will explode. If it's exactly equal to 0, then that means you have to do a little bit more work to investigate what the stability is, which we will eventually have to talk about. So that's all I put together for in terms of just these slides and things, and I think an hour is a good amount for that. So now we can just open this up to questions, comments. If anyone wants to look at specific any of the examples, we can work through them, or just talk about them. And if anyone needs to leave, I will send out the video link anyway, so you can always catch up then. So I figure we'll get maybe another half an hour or so. We can talk about general comments, ideas, questions, or exercises. How many of you have had a chance to look at the Strogatz book? A few. Okay, half of you, I guess. Yeah. So, is there anything?
Are you gonna lecture next week too?
I
would be happy to talk about bifurcations. It's like one of my favorite things ever.
Would you be willing to do it? That would save me a lot of time. So. Yeah,
like, I don't know.
That would be awesome. Yeah, if anybody wants to handle going through this, that would help a lot. Yeah. So yeah. Any topics anyone wants to bring up or examples? I'm going to exit this. The idea is we go kind of with these very, very basic ideas, and then by the time we reach 2 dimensions, we'll have a set of concepts. Bifurcations, the next chapter gets to stuff that's a little bit more complicated, but should be worthwhile when we talk about spiking models. Oh, and I have this spreadsheet I can share in case people didn't see it in the email. So if there's no other questions, comments, then we can close for now and meet next week. And Ryan will talk about bifurcations. Yes.
Yeah, if you have well, I can give my spiel about it, but I'm sure you also have some things you want to say.
I'm just picking out things that strike me from the Strogatz book, and just so that everyone has something to look at. I myself I haven't gone through any of this, which is part of the reason I wanted to do this, was just to make sure my foundation in this stuff is solid.
I like the bifurcation stuff a lot because it touches on singularity theory.
Nice.
And the work of Rene Thom, who's kind of like one of the progenitors of singularity theory and catastrophe theory, is like actually very close to the kind of a lot of topics that show up in my research. He has a book on morphology that I haven't read, but I guess like he dabbled in biology as well.
Yeah. We last year we did this Emergence Journal Club, and one of the things we talked about was catastrophe theory. And I think it was trendy for a little while in the 70s and 80s, and then I don't know what happened since then.
Mm-hmm.
But yeah, there was this demonstration of a switch that involved rubber bands. Have you seen this? I forget. Somebody named Zeman made it. I'll bring up a video of it next time.
Wait, I feel like
basically something switches from one attractor to another with, I forget what it's called. Karthik was here, he would remember.
Can I ask, what is singularity theory? Is there a short?
Oh yeah, go for it.
Yeah, so right, like there's kinds of
Did he drop out for everyone?
zero,
Yeah.
or it could be a place where
Ryan, your sound kind of dropped. Everything froze for a couple of minutes.
Uh-oh, he's visually frozen now
Yeah,
too.
looks like he's frozen.
Something is doing some bad mojo to his Wi-Fi.
A singularity in his internet connection.
Because yeah, had a
Man, you're still absent most of the time, Ryan. I don't know if you can hear this, but try to like get right on top of your Wi-Fi box.
I can hear you. Can you hear me?
It's getting better.
It's better now.
Okay. I feel like it's getting better for me too.
Okay.
Yeah, good. I think it's better now.
Okay, sorry about that. It goes off sometimes.
So yes, what's a singularity? First.
Yeah, I was going to say a singularity is a special point in some sense or another. There are many possible senses in which a point could be special. One very common is that, say you have a function, then a singularity could be where this function is zero, or it could be perhaps where the derivative of the function is zero. And those are very important, like what Yohan showed us, where say the fixed points in these one-dimensional dynamical systems, you could think about those as singular points, right? They're points whose behavior is special among all points. And kind of by knowing the singularities of your system, you learn about its structure. So singularity theory like takes this idea and amps it up a million times, where you start to think about like, how do you generally think about singularities of functions on manifolds or like maps between manifolds, and thinking about these in terms of dynamics as well. So there's a lot to it. Renee Thom was especially famous for kind of popularizing this idea that if you wanted to study the geometry of manifolds, one way to do it is to think about functions defined on the manifold and just take any function, look at where its derivatives are 0, and linearize the functions at those zeros, and then basically knowing these zeros and what their linearizations look like, you learn a lot about the topology of your manifold. So this is something called Morse theory.
So we can talk about it more, but maybe give people a quick kind of take home or message about, or what definition of what a manifold is and what topology is, because I know a lot of people hear those two words and get a little nervous, including some undergrad physicists. So.
Yeah, I was just giving you the the Wikipedia gloss over, but of course,
A manifold is something you attach to your car engine, right?
yeah, that's a good example of a manifold. I mean, most examples of manifolds are like round spheres or something. So I prefer to think about a manifold as something that has an interesting shape, because that's what it's supposed to connote, But it's a shape that's like, relatively uniform. So
or can you say something like, if you take a point on a manifold and then draw a small neighborhood around it, it sort of resembles a Euclidean surface.
Right. Yeah.
And just to link that back to the phase space idea, sometimes it makes more sense to talk about a constrained version of that state space where all the quantities of interest live, in this case, the derivatives. So I think that's where some of this comes from, that instead of talking about Euclidean space or something else, you talk about a manifold instead.
Yeah, usually people also talk about manifolds in the context of, I like to think of them as generalizations of surfaces. And so you can, like to Irvin's point, if you take a point and you draw a small neighborhood around it, or a circle or something like that, it looks like a Euclidean space, which is generally the case of like many spaces that are not globally Euclidean. But with manifolds specifically, the idea is that these spaces are sitting inside a larger Euclidean space of some sort. So it's like a sphere. The surface of a sphere is a manifold, because if you look at it closely, like Earth, for example, locally looks like a flat plane. But then globally, it has a much more complex and much more interesting structure together, sitting in a three-dimensional space. And then definitely in like many pop sci-fi stories, people talk about the universe being like a, multidimensional sphere, or the surface of a multidimensional sphere or something like that, sitting somewhere. Manifolds can be a good way of like playing around with that idea.
Does that mean a surface has to have curvature in order to be a manifold?
So generally the idea of studying manifolds is to find out whether there are curvatures to that space. So usually when people talk about manifolds, they develop it towards the theory of curvature. And sometimes it can just be a flat surface, or it can be like it will have zero curvature everywhere. Those are less interesting, but yeah.
But
so
that would, yes, that would be an ultimately boring manifold.
Not necessarily.
No.
An example of an interesting flat manifold is actually a torus. Not the usual torus that you picture as the surface of like a donut, but a torus which is like the coordinates in the plane where you periodically identify, say, x is the same as x plus 1, y is the same as y plus 1.
So you mean
a flat
torus where one of the coordinates, no, where both of the coordinates are periodic.
Right.
Okay. Interesting.
Neuroscientists sometimes use those kinds of boundary conditions when they're implementing models, so that you don't have weird boundary effects to do with inhibition and excitation. if you don't know what that means, we can talk about that eventually. I think once we cover 2 dimensions, we'll have a better feeling for all of this, and then we can, the hand waving will be a little less vague.
Is there a good like high level introduction to Morse theory?
That's a good question. I recently took a high school student through a summer course on Morse theory. I could send you the book that we used. I mean, it was definitely a math textbook, but
Yeah,
it's a relatively gentle introduction.
yeah, that would be great.
Cool. We talked about, okay, so singularities. There was one point I wanted to make related to information. So when you have singularities of the sort that we've already seen, or what Ryan kind of nodded to, it's places where the derivatives either go to 0 or to infinity. They could, depending on the context, they could be either of these. And in the case of the ones that blow up, in the context of, say, visual processing, you can think about derivatives in space as places where there are edges. And intuitively, what that means is that something is suddenly changed, and it was sort of not predicted by what was on the other side. Like if you have a nice, like a painting with a very black border on a white wall, nothing about the white wall predicts the fact that a black border is about to show up. So this is sort of related in a way to the attractor landscape, in the sense that in the places between fixed points, they're sort of boring in the sense that you know that it's a sort of and so on process, because it's just like, well, you place something there, it'll just go there. All of it can kind of be compressed in some loose sense into, but when you reach boundaries, you get what you might call the informative parts of a structure. So there is a sense in which information consists of the singularities in a space, in a visual space, in an auditory space. And this relates to compression also, because what you compress are all the parts that are the and so on parts. And you kind of keep track of as well as you can the singular parts, which are the most informative. Any other topics though, or we can wrap up and meet next time?
Something that would be useful for me is if people think of examples of these one-dimensional systems with attractors that are very simple and easy to have a math equation for, the like list of them, like the light switch, but similarly very simple examples that you could then sketch out the state space diagram for, I think. And so you could just see them one after the other would be useful for ones that are near the most simple, as least complexity as possible. I think that would be very helpful.
For people who are comfortable with some electrical engineering, an RC circuit would probably be like the best example. No momentum of any kind there.
I was thinking we could go through that, but I didn't put it in here. But it's a very, very simple system, and it is useful for neuroscience in the sense that a lot of rate-based models are equivalent to RC circuits. So what happens when you turn on the battery in that circuit is that basically the capacitor charges up. And then when you take the open the circuit or take the battery out, it discharges. The charging up to a fixed point and then the discharging are a way of modeling neurons that have an upper bound in their firing rate. So, Kale, that could be an example, if you like, of a fixed point. So if you imagine a really simple neuron that has an upper bound in its firing rate, while the input is on, it has an attractor, which is the asymptotic firing rate, around which it will be stable, depending on how you model it, because there's some quirks. But and then when there's no input, the firing rate will gradually come back down. There'll be an exponential fall off, and then the zero firing rate will be the attractor.
Are there any like persistent homology, like topology of data sets people here? Just wondering.
I recently started reading into that, and I like what I've read so far. I don't know whether I can use it myself, but I would like. I don't have enough topology understanding to maybe fully appreciate it, but it's something I definitely want to get into.
I remember this really cool, like, I guess you'd call it vision, but they were just studying natural image sets, and they looked at like 3x3 pixel patches. They were grayscale. So each 3x3 pixel patch is a point in a 9-dimensional like grayscale space. And they plotted these points, and they found that the points collect around something with the topology of a Klein bottle. And this is a really great puzzle. You can actually sort of give like you would never be able to guess this, I don't think, but you can give kind of like an ad hoc post hoc explanation of why it's a Klein bottle. But yeah, it's just
and this is in natural images, or
yeah. Let me try to find.
Yeah, if you could find that paper, that would be awesome. I recently read a few methods papers on persistent homology, and I would like to try and use them for analyzing cortical data, specifically images of stained tissue, because I think it may help with texture analysis, especially in textures that are stretched and squished with respect to each other. All this is
Image textures.
very tangentially related to dynamical systems, I suppose. But
yeah.
Let me end the recording here. And oh wait, is it recording? Yeah, okay. Yeah, well, it'll end.
It's from it's from the Carlson lab.
Is what? Anyway, I'm going to end
the paper that he just sent is from Gunnar Carlson. The